All right, let's start today's class. As I promised, today we are going to talk about efficient transformers, large language model, and the RUG. Today I'm going through, the ins and outs of the large language model, transformer, and large language model. Next week, I'm going to talk about the efficiency of large language model. How do you deploy them? Basically, all these, quantization, pruning, and all those distillation. What are the unique special optimizations we can do for large language models? Okay, so that's kind of the 2 weeks series. So, it's not working. All right, so ChatGPT. One of the large language models, Google Translator, this GitHub Copilot, and nowadays more and more all these large language model backed up applications, right? All these multimodal large language model, this visual language, you can take a picture and ask a question about it, right? So today we are going to talk about the transformers, transformer basics, some of the design variants, and the large language model with some advanced topics. Okay, so this is like kind of the main part. So in the first part, the transformer basics, we are going to go through all these different components and what are they. Okay. All right. So transformer basics. Um, before large language model, usually different tasks. People using different models for different tasks. For natural language processing, discriminative tasks such as like sentiment analysis, text classification, textual entailment. So basically, I give you this one sentence, and you want to tell yes or no, right? This kind of a discriminative native tasks. So we also have like this generative tasks, which given part of the sentence you want to generate, what's next, including like language models, translation, summarization. Before large language model, we have all these, RNNs, recurrent neural network. So the network kind of looks like this. You have the input, okay, and you have this hidden layer, and also you have this loop back, and then like this output. If you unroll this, like expand this network in real time, like during execution, it's more something like this. So when you are giving the network the first input, it's going to generate the first output. Meanwhile, it's also generating this red line output and the feed back to the network itself. Okay, so in the second step, you got a second input, but also you got the input from the first step. It's the same network, but previous step. Make sense? And then you are generating this output and generating the output, the red line for the next step. So you are doing this repeat over and over again to generate a sequence of outputs. Okay, so that's how recurrent neural network works. And this one essentially is kind of zooming view of this gray area. You kind of have the input, you have these red line come in and concatenate and go through the activation function. So that's kind of like what happened before. There are people propose many different kinds of recurrent neural network. LSTM being one of the famous. They have also many other like reservoir computing and all that different. But pretty much they follow very similar. They follow very similar idea. This 1D CNN is another way to do text generation. So instead of the image, you have like a two-dimensional kernel, right? For text input, you can have a one dimension kernel. So basically, it's like one, two, three, four. Let's say if let's say the kernel is 1 by 4, so this is the kernel. It's going to going through the inputs. Okay. So the similar idea, because for for 1D CNN, usually, when you are generating the output, it's not like in the recurrent neural network, it's a step by step. So you have very sequential. But in this one, you don't need to wait for the second input to come in. You can just look at all the inputs all at once, right? So you can have better scalability. Okay. But because oh, right, my laser pointer died. Um, but because um, you only the kernel, it's like it's a limited window, right? So the kernel can only look at this receptive field, right? And this is not like recurrent neural network, which kind of like can memorize like all your previous history. Does that make sense? So this kind of 1D CNN usually will have relatively limited context information because it cannot remember as much as the recurrent neural network. So the accuracy usually is not as good, but it can give you better scalability. Means that I can look at all the inputs all at once, and I can do a lot of parallel processing to make it faster. Okay, so these are just different pros and cons. Um, so this is two examples of recurrent neural network. This used for discriminative and the generative tasks. One thing I think like probably you can notice is that for on the left hand side, you can see the direction um, from this left and right between all these all those blocks. They are bidirectional. This is because for this kind of positive, negative, discriminative tasks, you can look at all the tokens all at once, right? You can look at all the inputs, and like they can have mutual communication to kind of give you the result. But for generative, which means that like usually you're looking at the previous text to generate a later text. So you can cheat by looking ahead, right? Because you don't know what is there. So that's kind of the why the architecture is designed like that. The problem also, but the problem with all these recurrent neural network is that it's very hard, even though like recurrent neural network can remember more than the 1D CNN, but it still has its own limit. So this one essentially is giving you this example. So if you look at the sentence like the chef who blah 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 was, right? So in order to correctly predicting that was, you need to memorize that chef is a singular word. Like it's not plural word. What if like you have a clause that's like super long, right? So the model needs to remember like all the way to that, and that's just not. Once the text becomes bigger and bigger, the network kind of just loses its memory. Okay, so that's the limitation of all these recurrent neural networks. That's that. So that leads to transformer. So there's this famous figure, attention is all you need. And attention by this we mean like one of the component, one of the central component in transformer. Okay, great. So we can use this. If you look at this transformer blocks a little bit a lot. So it's not. So we are going to break them down like into different small parts, and I'm going to explain like all these details. So, but let me first give you a very high level explanation, then I'm going to break into the details. So tokenizer is the one that where you feed the inputs into this. And then you see there are two towers, right? And then like these two towers, you see like there's one link between the top of the left tower to the right tower. Okay, and those are the two towers, and then the output comes out of the right tower. Okay, and let's first take a look at the left tower. So what the left tower has is that you have the tokenizer, and then like it's going to generate the token that's going to be used to generate the embedding. Again, I'm going to explain what is that. And then the embedding is going to be added to the positional encoding. Again, I'm going to explain what that is. And then like it's fed into this multi-head attention. So by multi-head, basically, it means that like you have multiple copies of the same thing. So let's just focus on one head. And then like you have this residual link, this added norm, and then this feed network, the feed forward network. Basically, it's a fully connected linear layer. Okay, nothing fancy. And then this added norm on the right hand side. And then we have this output encoding, positional encoding, and again tag, and then like, you have the link from the left hand side, like the left tower. You link them together, okay? And then you go to the feed forward, and this add a norm and linear and the softmax. So the output, like the output are pretty much the same as all the networks we've learned so far, right? You go through the linear layer and you go to the softmax kind of to do the selection. So from a very high level, the main idea of attention basically is that first of all, each sentence, for example, like attention is all you need, right? We can turn them into tokens. And for simplicity, let's just assume like each word is going to be one token. But in reality, it's not. Usually, sometimes like, for example, like comma, or like if the word is too long, you may break this into multiple syllables, and each syllable could be a token. Okay, but that doesn't matter. Let's just assume each word is a token by itself. And then like you are mapping that into this embedding. So what an embedding is essentially is a matrix, is a vector. It's a sequence of numbers to represent that word. So if like you were the architecture of this network, what is the simplest way you can think of to kind of do this encoding of the token? Let's say I have 100 tokens. What is the simplest way to just I give you like each token is going to be encoded by a vector. What is the simplest way? Everyone learned it so far. One hot, right? So one hot encoding is the easiest. So like let's say if I have 100 tokens, then I'm going to have like a vector of 100 dimension. Okay, and like then like each token has one place to be one. In this way, like you can have one single vector represents one token. Does that make sense? Okay. Now you understand, like now I have like 100 vector, each one is 100 dimension. Okay, that can perfectly capture these 100 tokens. And then like going through adding this positional encoding. What is positioning encoding? The reason is that well, if I say like I have a dog, okay, I have a dog. Then like I is the first position, dog is the last, right? If I do not have a positioning information in my tokens, what will happen is that the model will think I have a dog, it's exactly the same as dog has a eye. Because it does not know like where those words are. And these two sentences are going to be exactly the same looks to the model. Does that make sense? So that's why like we are going to have this positioning encoding. And what is the simplest way to have positioning encoding? We just assign what?
Like a hash map?
You don't even need that, like positioning encoding. You just need to remember the position of each word, right? So if you were the architecture, what would you do? Just assign what? 1, 2, 3, 4.
Just like an index.
Yeah. So you can just like have 1, 2, 3, 4 assigned to each token, right? And somehow you are combining that positioning information. For example, I'm just concatenating the position encoding into my vector. How about that? Okay, so that could kind of like give you the vector as well as like where the vector is, right? Right. So that both information you got. So now, if you have the position encoding, now like everything is so great. Then like I have a dog, the I will have the vector plus my position, right? But if it's a dog has a I, and then the I will actually have a different position encoding, the vector. So therefore, when the I appears in different locations, you will have a different encoding. Does that make sense? So therefore, like the model will know exactly where this I is. Does that make sense? So these two kind of look like the idea, the logic behind this is that so now like we can uniquely identify each token in which position. It's important, right? Because where the word is could be the objective or subjective. Like it matters to the text generation. Make sense? Okay. So now like we all understand it. So now I'm just going to give you this idea, but in reality, later you will learn like it's not that simple. But let's say like we were the architect, we are designing the model, and what we would think, right? The most intuitive way to design this. And then like the after adding the positioning and encoding, each token has its unique embedding. Then you are going to do this multi-head attention. Let's just focus on one head. On one head, the embedding itself is going to be multiplied with three different matrices. One encoding, let's say, attention. Okay. So the first word attention, its own vector. It's going to be multiplied with three different matrices. And you got three different vectors. Does that make sense? Attention, which is one token, multiplied with three different matrices. And you got three different vectors. Okay, and you do this for all the tokens. So it's again has three. All you need, each word is going to have three matrices now. Okay, what are these three? Oh, three matrices, and you are going to generate three different vectors for each single token. Okay, so what are these three different vectors? So we can just give a name. We'll give a name like there's a key, you probably heard of it, key, value, and a query. Okay, what is the idea? The idea is that the key and the value can kind of easy to understand. Like in the hash, you have a key and the value, or in the YouTube when you are searching, right? You are searching. It's going to be indexed. Like the first video is this, second video is this, right? So that's the key and the value. And what is the query? So the queue, well, the query basically says, oh, I want to look for a video with I don't know, kids in it. Okay, so then like you are going to kind of like matching the query with the index. See which video has kids in it, right? So you kind of like have this kind of a searching and matching thing to find which video has kids singing songs. Does that make sense? So that's the kind of like the idea of designing this query, key, and the value vectors. Okay, so then like the idea is that basically for each token, each word, each attention, for example, attention, you are going to have a value. So the value basically is the actual encoding of attention, the word attention. Okay, but also I'm going to have an index, which is the key, and I have a query, which is the key for the token. Make sense? So far so good? Okay. Then what attention does is that I'm going to build a table. Okay, I'm going to build a table. On the y-axis, like for each word, attention is all you need. On the x-axis, also attention is all you need. So I'm building up this table. Does that make sense? Okay. And after I have this table, I'm doing this so-called attention operation. So what essentially it does is that, for example, for attention, this word attention, okay, I'm going to use my query to do a dot product with all the keys of like all attention is all you need. I'm using query to do a dot product with all the keys. And what that means is that like, the kind of the idea is that how similar is my query with your index? Because if you do a dot product of two vectors, it's kind of like to calculate the angle between these two vectors, right? So to how similar they are. Does that make sense? So in this way, you can kind of like, to find like who I should be more related. If, for example, like, when I'm determined, like, should I, the form of the verb, should I use the singular or your plural? Then I need to look at my object, right? See, like, which one would then like I can determine which form I should use. Does that make sense? Kind of. So now it's very abstract, but later I'm going to actually give you a very good visualization of what's going on here. Okay? So now I just want to give you this high level idea. And then, by doing this, and on the right-hand side of the tower, it's also going through the same thing. But you may wonder why I have a input embedding and an output embedding. What's going on here? So remember, like in recurrent neural network, remember, like every time when we're trying to generate something, you are using the new input as well as the output from the previous step. Does that make sense? So for example, let's say like I'm trying to generate, let's say like the last word in the title, the need. I'm trying to generate the word need. Okay. So what do you need? Like when at that moment, like this model, what it looks at is that, well, the model itself has already generated, attention at all. Those are already generated by the previous steps. Does that make sense? And then like I'm looking at like you, then like based on what I generated before, based on what I'm looking at now, like then need is what I should generate. So therefore, this power is for the new input. This power is for the old output in the previous steps. Does that make sense? Kind of. It's okay. It's going to be very clear later. And then like, going through the same position encoding, going through the same attention. And then like you are doing another attention. It's called cross attention between the input and the output. Okay. And then go through the feed forward and linear and softmax. So I hope like kind of the high level logic is kind of clear here. Any questions so far? Yes.
So when you introduce the output embedding, is that what's giving it the long short-term memory? Essentially?
So you are trying to use the text you already generated and to feed it back to the model itself. So now I'm looking at the new input as well as the output I myself has already generated, because that was my output, my old output, to generate the next text. Make sense? Okay. Any other questions? All right. Next, so once like you kind of give you this relatively high level idea, then let's take a look at each of them. So first, like this tokenize the words, the word to tokens. A tokenizer maps a word to one or multiple tokens. For example, here 110 words be mapped to 162 tokens. So kind of like it's separated by each different color. You can see that like the second generative is kind of separated into generate. Okay. And even like the large language model. Well, but large language model, each word is a token. Okay. So that's kind of give you idea. And then like we need to map the token into embedding. And when we were designing this, I said like, what hot encoding is the easiest way to do the mapping, right? Which is true. So we can have this one hot encoding to do this. But the drawback of the one hot encoding is that like for 100 tokens, you need 100 dimensions because otherwise you're going to be repeating the vector, right? Right. So if the token, if the context, if the prompt becomes like very big, then like your vector dimension is going to explode. Okay. So apparently that's not a great design. It's a design. It's probably works in a small scale. Okay. But what's a better idea? So the word embedding is something that people have been using. So the idea is that map the word index to a continuous word embedding to a lookup table. So something like this. And the word embedding can be trained end to end with the model for the downstream tasks. Popular creation of word embedding includes the word tracks and globe. There are so basically we can use a pre-trained model to kind of train an encoder to map from the token to that vector. Okay. Any questions here? Okay. But have you guys ever thought about this? What is when we are designing like the good movie and you just randomly see those three real numbers, right? What is the reasoning? Is there any meaning behind this? What do you guys think? Or do you think it's just pure random? So if you look at the like giving three numbers, that essentially if you put that into the coordinator, essentially that's a three-dimension. It's at one point in the three-dimension space, right? But is that like really random? What do you guys think? Have you guys ever thought about this? I'm sure like you have been using these models one way or the other, but have you ever thought of what is the meaning behind all these vectorization? Why we are all these feature and all these tokenizer into embedding? Why we want to use why vector is a good way to represent a word? And this is actually a key. So this is actually a key concept in information retrieval. And the Google, like when Google first started, this is one of the main idea. If you think about it, in Google, if you were to build a search engine, okay, the web is so big, right? How can you do the index and quickly find something like you enter a keyword and find all the relative information? Like quickly find the relative information. Factorization is the key idea behind this actually. Okay, so let me actually, I find a really good video to explain the idea behind the vectorization.
Mentioned how those chunks are called tokens, which might be pieces of words or punctuation. But every now and then in this chapter, and especially in the next one, I'd like to just pretend that it's broken more cleanly into words. Because we humans think in words, this will just make it much easier to reference little examples and clarify each step. The model has a predefined vocabulary, some list of all possible words, say 50,000 of them. And the first matrix that we'll encounter, known as the embedding matrix, has a single column for each one of these words. These columns are what determines what vector each word turns into in that first step. We label it WE, and like all the matrices we see, its values begin random, but they're going to be learned based on data. Turning words into vectors was common practice in machine learning long before transformers, but it's a little weird if you've never seen it before, and it sets the foundation for everything that follows, so let's take a moment to get familiar with it. We often call this embedding a word. which invites you to think of these vectors very geometrically, as points in some high-dimensional space. Visualizing a list of 3 numbers as coordinates for points in 3D space would be no problem, but word embeddings tend to be much higher dimensional. In GPT-3, they have 12,288 dimensions, and as you'll see, it matters to work in a space that has a lot of distinct directions. In the same way that you could take a 2-dimensional slice through a 3D space and project all the points onto that slice, for the sake of animating word embeddings that a simple model is giving me, I'm going to do an analogous thing by choosing a 3-dimensional slice through this very high-dimensional space and projecting the word vectors down onto that and displaying the results. The big idea here is that as a model tweaks and tunes its weights to determine how exactly words get embedded as vectors during training, it tends to settle on a set of embeddings where directions in the space have a kind of semantic meaning. For the simple word-to-vector model I'm running here, if I run a search for all the words whose embeddings are closest to that of tower, you'll notice how they all seem to give very similar tower-ish vibes. And if you want to pull up some Python and play along at home, this is the specific model that I'm using to make the animations. It's not a transformer, but it's enough to illustrate the idea that directions in the space can carry semantic meaning. A very classic example of this is how if you take the difference between the vectors for woman and man, something you would visualize as a little vector in the space connecting the tip of one to the tip of the other, it's very similar to the difference between king and queen. So let's say you didn't know the word for a female monarch, you could find it by taking king, adding this woman minus man direction, and searching for the embeddings closest to that point. At least, kind of. Despite this being a classic example for the model I'm playing with, the true embedding of queen is actually a little farther off than this would suggest, presumably because the way that queen is used in training data is not merely a feminine version of king. When I played around, family relations seem to illustrate the idea much better. The point is, it looks like during training, the model found it advantageous to choose embeddings such that one direction in this space encodes gender information. Another example is that if you take the embedding of Italy and you subtract the embedding of Germany, and then you add that to the embedding of Hitler, you get something very close to the embedding of Mussolini. It's as if the model learned to associate some directions with Italianness and others with World War II Axis leaders. Maybe my favorite example in this vein is how in some models, if you take the difference between Germany and Japan and you add it to sushi, you end up very close to bratwurst. Also, in playing this game of finding nearest neighbors, I was very pleased to see how close cat was to both beast and monster. One bit of mathematical intuition that's helpful to have in mind, especially for the next chapter, is how the dot product of two vectors can be thought of as a way to measure how well they align. Computationally, dot products involve multiplying all the corresponding components and then adding the result, which is good since so much of our computation has to look like weighted sums. Geometrically, the dot product is positive when vectors point in similar directions. It's 0 if they're perpendicular, and it's negative whenever they point in opposite directions. For example, let's say you were playing with this model and you hypothesize that the embedding of cats minus cat might represent a sort of plurality direction in this space. To test this, I'm going to take this vector and compute its dot product against the embeddings of certain singular nouns and compare it to the dot products with the corresponding plural nouns. If you play around with this, you'll notice that the plural ones do indeed seem to consistently give higher values than the singular ones, indicating that they align more with this direction. It's also fun how if you take this dot product with the embeddings of the words 1, 2, 3, and so on, they give increasing values. So it's as if we can quantitatively measure how plural the model finds a given word. Again, the specifics for how words get embedded is learned using data. This embedding matrix, whose columns tell us what happens to each word, is the first pile of weights in our model. And using the GPT-3 numbers, the vocabulary size specifically is 50,257. And again, technically this consists not of words per se, but of tokens. And the embedding dimension is 12,288. Multiplying those tells us this consists of about 617 million weights. Let's go ahead and add this to a running tally, remembering that by the end, we should count up to 175 billion. In the case of transformers, you really want to think of the vectors in this embedding space as not merely representing individual words. For one thing, they also encode information about the position of that word, which we'll talk about later, But more importantly, you should think of them as having the capacity to soak in context. A vector that started its life as the embedding of the word king, for example, might progressively get tugged and pulled by various blocks in this network, so that by the end it points in a much more specific and nuanced direction that somehow encodes that it was a king who lived in Scotland, and who had achieved his post after murdering the previous king, and who's being described in Shakespearean language. Think about your own understanding of a given word. The meaning of that word is clearly informed by the surroundings. And sometimes this includes context from a long distance away. So in putting together a model that has the ability to predict what word comes next, the goal is to somehow empower it to incorporate context efficiently. To be clear, in that very first step, when you create the array of vectors based on the input text, each one of those is simply plucked out of the embedding matrix. So initially, each one can only encode the meaning of a single word without any input from its surroundings. But you should think of the primary goal of this network that it flows through as being to enable each one of those vectors to soak up a meaning that's much more rich and specific than what mere individual words could represent. The network can only process a fixed number of vectors at a time, known as its context size. For GPT-3, it was trained with a context size of 2048, so the data flowing through the network always looks like this array of 2048 columns, each of which has 12,000 dimensions. This context size limits how much text the transformer can incorporate when it's making a prediction of the next word. This is why long conversations with certain chatbots, like the early versions of ChatGPT, often gave the feeling of the bot kind of losing the thread of conversation as you continued too long. We'll go into the details of attention in due time, but skipping ahead, I want to talk for a minute about what happens at the very end.
So that gives you a very good explanation of that encoding, right? So, and at last it talks about, the initial GPT was trained at like 2048 tokens as the context. Next week, I started next week or next week, we're also going to talk about now, like people are trying to do this long context, trying to memorize your conversation history, right? So, but how do you, because when you are having a longer context, then like you need to do a lot of the attention computation. So like everything just, the overhead just increases. So people did a lot of optimization to trying to memorize as long as much, but also how to improve the computation efficiency. Okay, so that's the encoding. Let's get back to the slides. So now we learned that the vector kind of like can give you this index, and you can do the product to kind of find the similarity of these two vectors, and that's exactly what the Google is doing. Like you do all this vectorization of all these informations and the key, and then you have a vector for your keyword, right? And then you kind of like find like which vectors are more similar to your keyword, and those are then like they just rank all these web pages one by one. Okay, so that's kind of the key idea. Right. So and then like after we have this after we have this we left the positioning and coding to the last, but you already understand that it's encoding plus the positioning and coding, positional encoding, and you go to this multi-head attention. So this multi-head attention, inside of the attention, it looks something like this. So we are projected embedding E into query key and the value key KV. And by doing the projection, we need like three different matrices. Okay, one matrix for each token. You are going to multiply with this matrix to get your own Q, your own K, and your own V. Make sense? The QKV design is analogous to the retrieval system. Query is the text prompt. Key is the title description of the video. The value is the actual video. Okay. So if you look at let's look at the actual calculation of this attention over here. So the embedding goes through, transformation about three three different KV, QKV, and then like the inside the attention, each word you are using your own Q to attend with other words K. So as I described, when we are organizing the attention map, you have a table, right? So this y-axis, this x-axis, the rows and columns. So for each, if you look at the y-axis, for each word, you are using your Q to calculate with other, to append with other words key, to see how similar they are, and put the number inside that table. Does that make sense? Actually, I'm also going to show you a video, but table Q going to attend with other people's K, and then like do the attention, and then like going to a softmax, and that softmax is going to finally multiply with the other tokens V. So that kind of gives you basically gives you the idea of how related to capture like how related these two words are. Okay, and then like you are going to add. So if you remember, like we have that skip layer doing the adding by adding the original E with that V together, that added layer. So by doing this, remember like just earlier the video showed you that when you are when you are doing all this attention, so like if you have a king, then that's a very generic word, right? But the king inside a paragraph, there are a lot of kings. Okay, the Scottish king, Danish king, but each of them is actually has its own unique embedded in the space. So, but how do you know, like right now when I'm saying the king, like which king I'm referring to? So that's why like all this attention, by doing the attention king with all the surrounding contexts, you gradually pull the embeddings to other directions, which to finally to point to the unique king that you are referring to. Does that make sense? Does that make sense? So let me also use this this video to give you like a visualization of the attention.
In the last chapter, you and I started to step through the internal workings of a transformer. This is one of the key pieces of technology inside large language models and a lot of other tools in the modern wave of AI. It first hit the scene in a now famous 2017 paper called Attention is All You Need. And in this chapter, you and I will dig into what this attention mechanism is.
Right here. So this is what I'm talking about. So, well, it's all organized a little bit differently. But we are building up this table. And you can see that for each embedding, you have your own queue. And also, well, by the way, if you, both the column and it's the same sentence. It's called self-attention. So you can say like a fluffy blue creature rode the verdant forest. The same thing over there, right? And then like you can see like here like it's organized. The key has all these different rows. Okay, so you can see like each word has its own key. Each word has a key. Okay, and then like if you look at the word A. Let's look at the word A. Let's look at the column wise. So the first column, you can see that the Q1, which is the Q, basically the query for A, it's going to multiply with the K1. So basically says like how much I'm similar to my, how related QA is to the KA. Does that make sense? Okay. Then it's also going to calculate the Q1 with the K2, Q1 with K3. So all these things multiply together. Basically says, oh, how similar, this is me, this is my query, how similar your key is to my query. That's basically the semantic meaning behind this table. Make sense?
Visualizing how it processes data.
Oh, this is
As a quick
like
recap,
math.
here's the
This is a math channel. Like I highly recommend it. Explain a lot of the backgrounds of
important context I want you to have in
stuff.
mind. The goal of the model that you and I are studying is to take in a piece of text and predict what word comes next. The input text is broken up into little pieces that we call tokens, and these are very often words or pieces of words. But just to make the examples in this video easier for you and me to think about, let's simplify by pretending that tokens are always just words. The first step in a transformer is to associate each token with a high-dimensional vector, what we call its embedding. Now, the most important idea I want you to have in mind is how directions in this high-dimensional space of all possible embeddings can correspond with semantic meaning. In the last chapter, we saw an example for how direction can correspond to gender, in the sense that adding a certain step in this space can take you from the embedding of a masculine noun to the embedding of the corresponding feminine noun. That's just one example. You could imagine how many other directions in this high-dimensional space could correspond to numerous other aspects of a word's meaning. The aim of a transformer is to progressively adjust these embeddings so that they don't merely encode an individual word, but instead they bake in some much.
So this is also like a very good visualization. So you can see like all these attention animations on the top. What that essentially end up doing is that like, the original king's representation is a generic king. And by doing this attention with all other words, you're kind of pulling the vector to different directions. And by eventually, by attention with all the words in this whole paragraph, hopefully you can uniquely pinpoint to that unique specific king you are talking about. Does that make sense? So therefore, by doing this, therefore, that's why like attention is so smart that even the same word, like a king in this paragraph and the king in the other paragraph, the attention actually knows they are representing two different things. The same word in different context, the vector is going to point to different directions. So the model knows that they are representing, British king or, Danish king. Make sense? And all these attention and the add thing, essentially what is manipulating is this vector and eventually to point to the unique position. So that's why understanding the vectorization of this tokenizer, the token and the vector representation is essentially pretty much understanding all the machine learning models that you are dealing with, because that's kind of the main logic behind this.
Much richer contextual meaning. I should say up front that a lot of people find the attention mechanism, this key piece in a transformer, very confusing. So don't worry if it takes some time for things to sink in. I think that before we dive into the computational details and all the matrix multiplications, it's worth thinking about a couple examples for the kind of behavior that we want attention to enable. Consider the phrases American shrew mole, 1 mole of carbon dioxide, and take a biopsy of the mole. You and I know that the word mole has different meanings in each one of these, based on the context. But after the first step of a transformer, the one that breaks up the text and associates each token with a vector, the vector that's associated with mole would be the same in all.
So initially, the mole will be exactly the same. Okay, initially they are going to be, because it's a generic word, mole, right?
All three of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions as a function of the context. To take another example, consider the embedding of the word tower. This is presumably some very generic, non-specific direction in the space associated with lots of other large, tall nouns. If this word was immediately preceded by Eiffel, you could imagine wanting the mechanism to update this vector so that it points in a direction that more specifically encodes the Eiffel Tower, may be correlated with vectors associated with Paris and France and things made of steel. If it was also preceded by the word miniature, then the vector should be updated even further so that it no longer correlates with large, tall things. More generally than just refining the meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially ones that are quite far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how, after all of the vectors flow through the network, including many different attention blocks, the computation that you perform to produce a prediction of the next token is entirely a function of the last vector in the sequence. So imagine, for example, that the text you input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model's going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word was, will have to have been updated by all of the attention blocks to represent much, much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word. To step through the computations, though, let's take a much simpler example. Imagine that the input includes the phrase, "A fluffy blue creature roamed the verdant forest." And for the moment, suppose that the only type of update that we care about is having the adjectives adjust the meanings of their corresponding nouns. What I'm about to describe is what we would call a single head of attention, and later we will see how the attention block consists of many different heads run in parallel. Again, the initial embedding for each word is some high-dimensional vector that only encodes the meaning of that particular word with no context. Actually, that's not quite true. They also encode the position of the word. There's a lot more to say about the specific way the positions are encoded, but right now, all you need to know is that the entries of this vector are enough to tell you both what the word is and where it exists in the context. Let's go ahead and denote these embeddings with the letter E. The goal is to have a series of computations produce a new refined set of embeddings where, for example, those corresponding to the nouns have ingested the meaning from their corresponding adjectives. And playing the deep learning game, we want most of the computations involved to look like matrix vector products, where the matrices are full of tunable weights, things that the model will learn based on data. To be clear, I'm making up this example of adjectives updating nouns just to illustrate the type of behavior that you could imagine an attention head doing. As with so much deep learning, the true behavior is much harder to parse because it's based on tweaking and tuning a huge number of parameters to minimize some cost function. It's just that as we step through all of the different matrices filled with parameters that are involved in this process, I think it's really helpful to have an imagined example of something that it could be doing to help keep it all more concrete. For the first step of this process, you might imagine each noun, like creature, asking the question, "Hey, are there any adjectives sitting in front of me?" And for the words fluffy and blue to each be able to answer, "Yeah, I'm an adjective and I'm in that position." That question is somehow encoded as yet another vector, another list of numbers, which we call the query for this word. This query vector, though, has a much smaller dimension than the embedding vector, say 128. Computing this query looks like taking a certain matrix, which I'll label WQ, and multiplying it by the embedding. Compressing things a bit, let's write that query vector as Q, and then anytime you see me put a matrix next to an arrow like this one, it's meant to represent that multiplying this matrix by the vector at the arrow's start gives you the vector at the arrow's end. In this case, you multiply this matrix by all of the embeddings in the context, producing one query vector for each token.
So remember the WQ is exactly the same for all the tokens, but because the embedding was different, so you are generating different Qs.
The entries of this matrix are parameters of the model, which means the true behavior is learned from data, and in practice, what this matrix does in a particular attention head is challenging to parse. But for our sake, imagining an example that we might hope that it would learn, we'll suppose that this query matrix maps the embeddings of nouns to certain directions in this smaller query space that somehow encodes the notion of looking for adjectives in preceding positions. As to what it does to other embeddings, who knows? Maybe it simultaneously tries to accomplish some other goal with those. Right now, we're laser focused on the nouns. At the same time, associated with this is a second matrix called the key matrix, which you also multiply by every one of the embeddings. This produces a second sequence of vectors that we call the keys. Conceptually, you want to think of the keys as potentially answering the queries. This key matrix is also full of tunable parameters, and just like the query matrix, it maps the embedding vectors to that same smaller dimensional space. You think of the keys as matching the queries whenever they closely align with each other. In our example, you would imagine that the key matrix maps the adjectives, like fluffy and blue, to vectors that are closely aligned with the query produced by the word creature. To measure how well each key matches each query, you compute a dot product between each possible key-query pair. I like to visualize a grid full of a bunch of dots, where the bigger dots correspond to the larger dot products, the places where the keys and queries align. For our adjective-noun example, that would look a little more like this, where if the keys produced by fluffy and blue really do align closely with the query produced by creature, then the dot products in these two spots would be some large positive numbers. In the lingo, machine learning people would say that this means the embeddings of fluffy and blue attend to the embedding of creature. By contrast to the dot product between the key for some other word, like the, and the query for creature, would be some small or negative value that reflects that these are unrelated to each other. So we have this grid of values that can be any real number from -infinity to infinity, giving us a score for how relevant each word is to updating the meaning of every other word. The way we're about to use these scores is to take a certain weighted sum along each column, weighted by the relevance. So instead of having values range from -infinity to infinity, what we want is for the numbers in these columns to be between 0 and 1, and for each column to add up to 1, as if they were a probability distribution. If you're coming in from the last chapter, you know what we need to do then. We compute a softmax along each one of these columns to normalize the values. In our picture, after you apply softmax to all of the columns, we'll fill in the grid with these normalized values. At this point, you're safe to think about each column as giving weights according to how relevant the word on the left is to the corresponding value at the top. We call this grid an attention pattern. Now, if you look at the...
Or sometimes like attention map, heat map, you'll see a lot of different mentioning of this table. But the idea is that like how they are related or attended.
Original Transformer paper, there's a really compact way that they write this all down. Here,
so that's the equation. So like now, like with that animation, I hope you understand this equation much better. So you can see that how you have the Q and the K divided by, well, it's normalized by the square root of dk, the dimension of K, and then go through softmax. That's the final, that's the table we just saw. Okay.
Variables Q and K represent the full arrays of query and key vectors, respectively, those little vectors you get by multiplying the embeddings by the query and the key matrices. This expression up in the numerator is a really compact way to represent the grid of all possible dot products between pairs of keys and queries. A small technical detail that I didn't mention is that for numerical stability, it happens to be helpful to divide all of these values by the square root of the dimension in that key query space. Then this softmax that's wrapped around the full expression is meant to be understood to apply column by column. As to that V term, we'll talk about it in just a second. Before that, there's one other technical detail that so far I've skipped. During the training process, when you run this model on a given text example, and all of the weights are slightly adjusted and tuned to either reward or punish it based on how high a probability it assigns to the true next word in the passage, it turns out to make the whole training process a lot more efficient if you simultaneously have it predict every possible next token following each initial subsequence of tokens in this passage. For example, with the phrase that we've been focusing on, it might also be predicting what words follow creature and what words follow the. This is really nice because it means what would otherwise be a single training example effectively acts as many. For the purposes of our...
So this is something called autoregressive. So what that means is that first, if you think about like this model itself, first you are feeding the word the, right? And then that will give you fluffy. And then the next time you're actually running the model again, but by feeding the fluffy into the model. So when you want to predict this whole sentence, actually every token you are predicting, you run this whole model once. Does that make sense? So this is a very labor-intensive process to predicting this whole sentence. So that's this so-called autoregressive.
Attention pattern, it means that you never want to allow later words to influence earlier words, since otherwise they could kind of give away the answer for what comes next. What this means is that we want all of these spots here, the ones representing later tokens influencing earlier ones, to somehow be forced to be 0.
What that means is that, for example, if you think about it, if you look at the first column, which is right, a fluffy A. So what that means is that we don't want the A to look into the future. So A can only attend to itself, but not fluffy, not blue, not the rest of it, because it can't cheat to look into the future. Okay, but the last column, which is the forest, when we are trying to predict what's after the forest, then like the forest can look at everything has already happened so far. So that's why the forest can attend to a fluffy blue creature rodent in the verdant. Does that make sense? So that's why this is so-called when we are doing this generative task, this so-called masked attention by masking the future. For every token, mask the future tokens. So you only got half of the attention map. Does that make sense? So, but this is not necessary if you are doing this discriminative tasks, right? If you like, wow, the movie is great. Is the sentence correct or not? Then like the model can look at the whole sentence no matter which direction it is. Does that make sense? So only in generative models, usually we have this half masked attention map. If it's a discriminative task, you can look at the whole you have the whole attention map, and that's even better actually. Does that make sense?
The simplest thing you might think to do is to set them equal to 0, but if you did that, the columns wouldn't add up to 1 anymore. They wouldn't be normalized. So instead, a common way to do this is that before applying softmax, you set all of those entries to be negative infinity. If you do that, then after applying softmax, all of those get turned into 0, but the columns stay normalized. This process is called masking. There are versions of attention where you don't apply it, but in our GPT example, even though this is more relevant during the training phase than it would be, say, running it as a chatbot or something like that, you do always apply this masking to prevent later tokens from influencing earlier ones. Another fact that's worth reflecting on about this attention pattern is how its size is equal to the square of the context size. So this is why context size can be a really huge bottleneck for large language models, and scaling it up is non-trivial.
And that's just like very little, right? So if you think about like the initial version, the context of 2048, so that's 2048 by 2048, and now like context is even bigger. So the context means that like the more history, for example, if you are chat with the chat GPT, that means that like the GPT can remember how much history you have already talked with it. Okay. Of course, like the longer the better for us, right? But computation wise, it's not. It's explore like, you know.
As you might imagine, motivated by a desire for bigger and bigger context windows, recent years have seen some variations to the attention mechanism aimed at making context more scalable. But right here, you and I are staying focused on the basics. Okay, great. Computing this pattern lets the model deduce which words are relevant to which other words. Now you need to actually update the embeddings, allowing words to pass information to whichever other words they're relevant to. For example, you want the embedding of fluffy to somehow cause a change to creature that moves it to a different part of this 12,000 dimensional embedding space that more specifically encodes a fluffy creature. What I'm going to do here is first show you the most straightforward way that you could do this, though there's a slight way that this gets modified in the context of multi-headed attention. This most straightforward way would be to use a third matrix, what we call the value matrix, which you multiply by the embedding of that first word, for example, fluffy. The result of this is what you would call a value vector, and this is something that you add to the embedding of the second word, in this case, something you add to the embedding of creature. So this value vector lives in the same very high-dimensional space as the embeddings. When you multiply this value matrix by the embedding of a word, you might think of it as saying, if this word is relevant to adjusting the meaning of something else, what exactly should be added to the embedding of that something else in order to reflect this? Looking back in our diagram, let's set aside all of the keys and the queries, since after you compute the attention pattern, you're done with those. Then you're going to take this value matrix and multiply it by every one of those embeddings to produce a sequence of value vectors. You might think of these value vectors as being kind of associated with the corresponding keys. For each column in this diagram, you multiply each of the value vectors by the corresponding weight in that column. For example, here, under the embedding of creature, you would be adding large proportions of the value vectors for fluffy and blue, while all of the other value vectors get zeroed out, or at least nearly zeroed out. And then finally, the way to actually update the embedding associated with this column, previously encoding some context-free meaning of creature, you add together all of these rescaled values in the column, producing a change that you want to add that I'll label delta E, and then you add that to the original embedding.
See, so that's how the original embedding, let's say like the king, got attended with all these context and got that delta E, so it's dragged to the unique direction that we want. So that either be it like British king or Danish king, that's how it's dragged to the correct representation. Make sense? That's the whole point of doing attention.
Hopefully, what results is a more refined vector encoding the more contextually rich meaning, like that of a fluffy blue creature. And of course, you don't just do this to one embedding, you apply the same weighted sum across all of the columns in this picture, producing a sequence of changes. Adding all of those changes to the corresponding embeddings produces a full sequence of more refined embeddings popping out of the attention block. Zooming out, this whole process is what you would describe as.
So for example, like if let's say like a word blue, so blue should be like, well, it could be like different degrees of blue, right? But if it were not like in the context, if it's like there's no degree of blue, then like the blue should not be changed too much. Does that make sense? But if it's like a creature here, like then you are tending with the fluffy and the blue, then that embedding probably will be changed a lot to by port to a different direction. Does that make sense?
A single head of attention. As I've described things so far, this process is parameterized by three distinct matrices, all filled with tunable parameters: the key, the query, and the value. I want to take a moment to continue what we started in the last chapter with the scorekeeping, where we count up the total number of model parameters using the numbers from GPT-3. These key and query matrices each have 12,288 columns, matching the embedding dimension, and 128 rows, matching the dimension of that smaller key query space. This gives us an additional 1.5 million or so parameters for each one. If you look at that value matrix by contrast, the way I've described things so far would suggest that it's a square matrix that has 12,288 columns and 12,288 rows, since both its inputs and its outputs live in this very large embedding space. If true, that would mean about 150 million added parameters. And to be clear, you could do that. You could devote orders of magnitude more parameters to the value map than to the key and query. But in practice, it is much more efficient if instead you make it so that the number of parameters devoted to this value map is the same as the number devoted to the key and the query. This is especially relevant in the setting of running multiple attention heads in parallel.
So what we just saw was just one attention. Then like when you are duplicating this multiple attention head. So remember when you are training the model, all these different heads is going to have its own query key and the value matrices. So therefore, when the same token going through multiple heads, you are actually mapped to different embedding. Does that make sense? And the why like adding multiple heads helps. Like one way to think about it is for example, like let's say like one head is trying to capture the color dimension information, and the other head is trying to capture like the shape dimension of the information. So multiple heads is trying to capture different part of the semantic meaning by doing like relation with other contexts. So by doing this, like you can have capture more related information from all your contexts. Okay, so that's the idea of why we are adding multiple heads. Remember, their weights are different so that they can capture different aspects of the relationship.
This looks is that the value map is factored as a product of two smaller matrices. Conceptually, I would still encourage you to think about the overall linear map, one with inputs and outputs both in this larger embedding space. For example, taking the embedding of blue to this blueness direction that you would add to nouns. It's just that it's broken up into two separate steps. The first matrix on the right here has a smaller number of rows, typically the same size as the key query space. What this means is you can think of it as mapping the large embedding vectors down to a much smaller space. This is not the conventional naming, but I'm going to call this the value down matrix. The second matrix maps from this smaller space back up to the embedding space, producing the vectors that you use to make the actual updates. I'm going to call this one the value up matrix, which again is not conventional. The way that you would see this written in most papers looks a little different. I'll talk about it.
Okay, so I think that's good. So that hopefully now like you have a very vivid idea of what's going on with all these attention process. Okay. So now if you look at all these abstract math representation, you should clearly know like what's going on here. Uh, that's pretty much the table we just showed you earlier. And that's the multiple heads. Okay. And then you can like this slide is trying to visualize the attention map for different heads, and you can see they are a little bit different because they are trying to capture different part of the relationship. What is this? So this is the global self-attention and the masked attention, the half attention. You may notice this is a little bit different. It's a little bit flipped, right? Because in this one, the query is organized here, the key is organized here. It's a little bit different from the video, but the idea is the same. So the causal means are like we need to look at the previous message, not the later ones. So that's why we need it. But the global means that we can look at everything all in one C. Okay. Okay, so let's take a break here. Let's come back at 7:25. Okay.